Hi, in this video I will try to explain you how you can use DEScan2, which is likely an alternative to a DiffBind package. Both of those packages are used for differential analysis of peaks like ATACseq, ChIPseq and others. Why would you want to use DEScan2? In principle, DiffBind is a good package, but it requires at least 3 samples per group, and sometimes you don't have those 3 samples. If you have only 1 sample per group, you can do only comparison absent present, and that's it, draw Venn diagram. But if you have 2 samples, it's excessive for Venn diagram and too little for a DiffBind. What to do then? This is the case when you can consider using DEScan2. How DiffBind operates? First, it takes bed files and makes a table of those consistent peaks through the samples. It counts reads per peak using BAM files. Then it uses HR or DEScan2 integrated, so you're not freely communicating with HR on DEScan, you communicate with a DiffBind package which is using functions out of those. It also provides plenty of gadgets and plots, normalization, filtering of some blacklisted peaks and so on. It doesn't provide annotations, so the results are differential peaks with the coordinates in a genome, no gene names. If you want gene names, you have to stick a ChIPpeakAnno to your resulting table and then do the rest in ChIPpeakAnno. So what DEScan2 offers, it also takes and makes table of consistent bed files. You only don't need to make a sample file. You can simply indicate directly where they are. You also indicate where you have a BAM files, in which directory, and then it will read count reads per peak. And this is actually the end of the story. After creating this read count table, you can save it and then use regular HR on DEScan package by yourself using your common knowledge. And of course there are some extra gadgets and suggested options to the regular HR and DEScan protocol. You can take it or leave it, it's up to you. DEScan2 package is located in bioconductor, just like a DiffBind package. And whereas tutorial for DiffBind is pretty long, the description how to use DEScan2 is not that long. I wish it was. Let's check the suggested lines. First you load the libraries, the DEScan2 itself, this is a helper, and HR as a separate package. The very first line is reading BAM files. Why? Because authors offer you a possibility to do a peak calling within a DEScan package, which is in the next line, but I wouldn't do it. First of all, when I tried it, my RStudio crashed. I don't know how powerful is their computer, probably much more powerful than mine. And secondly, I do have my bed files already, why can't I use them? Next, authors open a system file which looks like a bed file, which is not helpful if you want to open the real one. Anyhow, after the next line, final regions, you see a list of peaks and the whole format looks like G-ranges. And at the end, the final table appears over here, count final regions, and you do it by reading BAM files, and that's it. And then at the end, you're supposed to have something like this. That's the final table. And then you can do nice figures, normalizations, PCA plots, which you can do anyway. And this part is a direct quote out of HR, more or less, with some modifications, but even without would work as well. I must admit it took me some time to figure out how to use this package with the real data. For my exercise, I took a part of the data from NCBI Geo, this one. It is a set which you cannot use in DiffBind because everything is in two replicates, but that's a nice opportunity to try DEScan2 and HR. Out of those data, I took only DMSO and TCP. I do not want to run ahead of the author's analysis and conclusion, so those 4 files are enough. That's what I downloaded, mapped, created, sorted BAM files, bed files, of course, ready to operate. First, I add this BIOC parallel multi-core. It is recommended, and I agree, some steps are slow. Then I import libraries DEScan supporting HR on its own for differential analysis and ChIPpeakAnno for annotation. Nice. So, following my own logics, I begin with the reading bed files. These are just names of them yet, and now the names will be short part, the front one, like this. And now in a loop I assign every content of a bed file to every name. Have 4 sets of data with a modification in a strengths, etc., etc. Out of which I create a bed list as a granges list. That's the way how you can import bed files into this script. This is the missing line which I had to figure out, because if I don't do it, then it complains about missing names and give an error. And now I integrate all the bed picks, and it takes some time. It took me 3 minutes. Alright, this line is done. It complained about this context, which you actually can remove right at the beginning or wait until the end. Anyway, now we count final regions using BAM files, and you simply tell where are they, and you do not annotate. It will cause only error, and annotation is not needed at this step. And it is another slow step, if I remember well. Yeah, another 2 minutes. These are the only 2 slow steps. The rest is reasonably good. This line is the last one needed to create a table of counts per pix. You extract it in this line. You rename the column names because it incorporates all the directory and the full name of the BAM file. Far too long. Check again that's the proper column names. And then the work for this package is basically done. You have a counts table, and then you have regions, which is a granges file with the extra information and more readable coordinates of every peak. That's what you will need for annotation. I didn't do it before, I do it now. I remove all these nasty contigs and keep only chromosomal locations. And then I come to F counts and F regions, meaning filtered. Then, because the script was designed for internal bed files which have a slightly different structure, some columns are empty and you remove them, you see that this column and the next one and the next one is 4 empty columns. We don't need them. And the business for the DEScan2 package, strictly speaking, is done here. You save the results. First of all, table of counts and table of row names. With this, you can move to differential analysis. So this part is very much like HR tutorial, and you can read and apply everything you know from the HR vignette. They suggest this normalization, which is slightly different. You can do it. Then you create this, what is called model matrix, these lines. Then you can check this RLA, which is relative log expression, compare between samples, but this is real ugly. Don't try to improve it. Instead, I would suggest use VOL plot, which is much nicer. And you can do PCA plot, why not? With this distribution, you would not expect a long list of differential peaks. There is a step of removing unwanted variations in DEScan2, which you can try, but it didn't work for me. It complained and made errors in the later steps of fitting, and therefore I didn't use it. So I make my design, which is very simple, 2 groups, 4 samples. Then I declare DJ list, just as it's very usual. That's my line. I prefer to filter by expression low counts. They never give anything good. Then estimate dispersion and fit. That's the latest recommended option. Then check the design. Treatment DMSO, treatment TCP, that's my contrast, test, top tags, results, summary. The list of differential peaks is short as expected. For our exercise, a smaller results table even better because it's easy to read, and this is what we do. Create a tops table. This is what it is. Check the directory, where am I? Write the table. So this part is done. What is left is annotating peaks. There are no gene names, but we like to know near which genes are those peaks. It can be done with the ChIPpeakAnno package. First we load row names of peaks. Then we reduced the list by filtering it to the tops, what we just created. Then we merge one with another. And then we convert it to G-ranges, because everything works through G-ranges in a ChIPpeakAnno. There are many ways of calling annotation. This data belong to Homo sapiens, and I mapped it using assembly version 38. For simplicity, I used the library version of it, but I can show you in another video how you can use your own annotation which you use for mapping. So you declare what's the map, then you call for annotation, and you say max gap 1000 is close enough to the feature type transcription start. Okay, so the features here look like entries, gene IDs, therefore you have to convert them into the real gene names. Again, there are different possibilities. I use the simplest one, importing org HSEGDB library. So add gene ID, feature type entries. What I need is symbol. And now it's still a granges format, but with gene names in it, and you can say I want a data frame format so I can read it, and here we are. First peak coordinates, then number of peaks in your samples. It means, for instance, that 3 bad files had this peak, and here we had a 4, which means they're actually always present, but the read counts per group are significantly different. And at the end you have your favorite symbol of the gene. Basically everything you want. And you save this final data table, and the job is done. To summarize this story, what can I say? DEScan2 works, but you have to know how. Unfortunately, vignette is not very helpful. The script should follow 3 steps. First, you create peak counts table from your bat and BAM files. Then second, perform differential analysis. It has little to do with the DEScan2, it's more HR and DSEQ2. And third step is annotate differential peaks with ChIPpeakAnno, which is another package again. And if you put all these steps together, it will work for you. I'm not sure, although, how it will work with a bigger number of samples. I tried it with 4 samples, 6 samples, but if there are 10 or 20, then I have some doubts how it will perform. Some steps are really slow. That's more or less what you have to know about DEScan2. And thank you, until next time.